We first got into machine learning in the interest of accelerating discovery of open shell transition melt complexes and catalysts and materials, and trying to apply machine learning to spaces where we knew, say, affordable computational chemistry would fail. There were no fast ways to screen large spaces of transition melt complexes. I'd say a more emerging area for my research group, so we still work plenty in that area, is trying to understand what does it take to be an expert in computational chemistry. So what normally takes a PhD to just figure out how to run a good electronic structure calculation, how to tell good data from bad data, and how can we encapsulate those decisions and that knowledge in machine learning, artificial intelligence models. And what motivated us to go into that space is because in our work, a lot of the times we're having machine learning models pick for us new materials to simulate. And those machine learning models on their own, they're just property prediction models. They won't know if we're traveling into a space where the method that they're trained on is not predictive, or where that material is just not a physically feasible material. So and having been a PI for several years, I know how hard it is also to just train someone in terms of knowing what parameters are meaningful to set up a good physics-based electronic structure simulation. When should we trust the simulation? And so we've seen a lot of promising opportunities there to start to simplify and make accessible computational chemistry in cases where people still want to say run a density functional theory calculation, but with knowledge of and guidance from the machine learning model about what is a good calculation to run.
I mean, my lab is getting nuts. I mean, we have I think we have 30 collaborations approximately right now. I have 25 students and postdocs and undergraduates. And we work everywhere from catalysis, kind of traditional catalysis, where we run our own reactions in the group, to, let's say, coordinating a process optimization in a big pharma firm, to more recently trying to figure out how to use the tools that we've been developing in enzymatic optimization. And most of the areas we work in today, none of these projects existed 4 years ago, and it really connects back to the simple kind of philosophy the group had for the first half of the 2000s, which was, how do you featureize or develop descriptors for small molecule catalysts? And that's all evolved now into a program where we have people writing code, which, again, I'm a synthetic chemist. I don't know how to even write code myself. We rely heavily on computations, including we're now doing MD. Again, I am not a trained computational chemist. My students and postdocs make this happen. So I didn't really answer your question precisely, because I can tell you that the number of projects we're running these days is overwhelmingly difficult. I actually have a spreadsheet to keep a track of what's going on. And I happen to be department chair, so I have a spreadsheet for that too. So I barely know what's going on in my group, but I can tell you that they're kicking butt. It's a spectacular team.
So we've tried to pull together a pretty diverse list of chemists who, especially a large number of them, started in more traditional fields and have really advanced and pioneered and leveraged data science techniques. This isn't the first decade in which this has happened. Back in the 80s and 90s, a lot of people were thinking about data science, but I think the accomplishments that have happened in the past 10 years have really positioned themselves to transform how all of us are as chemists, in terms of the way in which we think about building structure property relationships, or discovering new materials, or even building force fields and electronic structure models. And I know Matt and I have tried to curate a list of people who come from experimental materials, chemistry backgrounds, and have really, we believe the issue will showcase the ways in which people have really started to leverage data science techniques in a way that gives a broad view of the field.
I mean, I think the simple answer is people should always read accounts, because it's my favorite journal to read. I mean, where you actually read the article, don't just look at the pictures. because it's always interesting. And so for, let's say, this issue, it's an incredibly disparate group of authors in pretty broad areas of chemistry. It's the most broadly defined, I think, issue you could have. This is what I love about data science. It has no borders in chemistry. There's every area of chemistry is going to be touching in this area in the next decade, in my opinion. And so counts as a great place to put in the first kind of round of these types of stories. And 5 years from now, or so, it'd probably be smart to see where this is all gone and do another issue of this sort. Yeah, so accounts rocks.